Okay. So Cobb-Douglas utility functions is quite an important function that you have to learn in microeconomics. So let's spend some more time talking about some important properties of it. So the first thing to realize is that Marshallian demand function from a Cobb-Douglas utility, symbol here x2 start, only depend on P2, so it's all price, and not depending on P1. So the other goods. Doesn't matter if P1 changes or stay the same, the demand of X2 will not be affected. That means no cross-rate effect. Now, what happens when we keep the price of X2, like P2, fixed, but we adjust the price of X1? Let's say decrease P1. We talk about it, right? So if P1 decrease, the point where the budget is exhausted by spending on X1 will move further to the right, but nothing happens with the intercept, right? At this point. Then every time your budget line moves or less steeper, then to get to a higher utility level, the indifferent curve, which is now tangent with the new budget lines change. Consequently, you get a new optimum point, which is here now, and here now, and there. Yeah. So if you connect these optimum points every time px1 change, you will get a horizontal line, like here, the dotted line. Now, so that is, there's no cross price effect. Every time your new optimum point changes, the optimum consumption of X2 will remain the same. Let's move on the second property, which has to do with the income expansion path. So what is income expansion path? It is the line connecting all the optimum points when income changes. So here, let's say your original budget line is that line over here. And then what happens when your income increases? Remember, there will be a shift outward parallel to the original budget line, right? And every time you shift to a new budget line, your optimum point will change, right? Because you on a different curve every time. And when you connect all those optimum points over here, 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 sorry, you get a curve. This is called income expansion path. In the case of the Cobb-Douglas utility, is a linear path, so it's not a curve. But in many other cases, is the curve. Why can we say that the linear is linear in this case? Let's look at this equations. This is something we got on the way when we derived from the first order condition of utility maximization, right? At one point we had this already. So now you could also solve for x2 as a function of x1 and all other parameters. So the exponent, p1, p2, yeah. do that on your own if you feel like practicing a bit more. Then this result, when you solve for x2 as a function of x1 from this equation, is the expansion path equation. And what is the slope of this income expansion path? So you take the derivative again of x2 with respect to x1, which is 1 minus a over a times p1 over p2. So this equation shows that it's a linear function, so that will be a line. The second thing to realize, the intercept now is 0, right? You have only one term associated with x1. So the first thing is a line, linear expansion path. The second thing is goes through the origin. That's the income expansion path of the Cobb-Douglas utility function. Very special. So there's several more important properties of the Cobb-Douglas utility function that we talk about here on slide 22. Let's see it clearly. Now, again, this is the Marshallian demand function of x1 that we have solved, right? Let's write it this way so that it's easier for us to derive the properties later. So it should be p1 to the power minus 1, right? The first thing is income elasticity. Elasticity, which is denoted as epsilon x1 with respect to I, right? So this income elasticity is, by definition, the derivative of x1 start with respect to income times income over x1 start, right? So now the derivative of x1 start with respect to income, let's say I to the power 1. So treating everything else constant, that means we have a times p1 to the power minus 1, and then we times I, this is the derivative, and this is, now we write, coming to the next part, we write I over x1 start, but now we plug x1 start as a function of the parameters again over here. So that is a times I times p1 to the power of minus 1. Let's simplify things. A is gone, I is gone, p1 to the power of minus 1 is gone. So at the end is equal 1, right? So this is the first property, income elasticity of the Marshall demand function on the Cobb-Douglas utility is 1. That means when when income increases 1%, the consumption of the good will also increase 1%. And that is constant, doesn't matter how much you're consuming already. That's the first thing. The second thing is the oil price elasticity. Which is, again, X1 start, and here is P1 now, right? By definition, that is the derivative of X1 start with respect to P1 times P1 divided by X1 start again. So look at this. Now the derivative of X1 start with respect to P1 will be, because the exponent is minus 1 goes first, times A and I constant, times P1 to the power of minus 2, right? And then times P1, rewrite it again here, over A times I times P1 to the power of minus 1. Simplified. Minus 2, here is 1, plus 1, so minus 1 and minus 1, so it's gone. Every piece gone. A gone, I gone. At the end, that is minus 1 left, right? So the out price elasticity of the Marshallian demand function in the Cobb-Douglas case is minus 1, meaning when the price of X1 increases by 1%, the consumption of X1 will decrease 1%, and that's also constant. Doesn't matter how much you're consuming already. You could also try these properties to derive the properties for X2 start, for example, as an exercise to yourself. So the third one is the expenditure share. So expenditure share by definition is denoted by S, small s, 1, which is the amount that you spend on X1, which is P1 times X1 start, divided by your total income. So in that case, let's plug things in. P1 times X1 start is A times I times P1 to the power minus 1, right? And divided by I, which means what? Which means times I to the power of, sorry, this is probably too ugly, minus 1, right? So now, simplify again, I to the power of 1 and minus 1 is gone, P to the power of minus 1 and P to the power of 1 gone. At the end you only have A left, which is exactly the exponent of X1 in the utility function before. So the expenditure share, in this case, constant for the goods under Cobb-Douglas utility. And this is something different from the angle law. So what does angle law say? But first let's talk about the angles curve. So the angle curve is normally would be like this. Under angle law, the law say that when your income increase, your consumption of good, the budget share you spend on good, will decrease. This is not probably the best draw because it should not show an increase here. So the angle curve in this case will be concave. What is the angle curve? The angle curve. Actually, the angle curve is the curve which shows different level of consumption of the goods. Here X1 with different level of income. So that curve for food normally should be concave, nah? Because your consumption increase with income increase, but it increase lower, much lower than the speed of income increase. That's why the share decreases when income increase. However, with the Cobb-Douglas that we just derived here, the budget share always constant. So that means the slope of the angle curve is constant. In the case of the Cobb-Douglas. CD utility. The angle curve is linear. You can actually see from the demand function already. So as income is like the linear function and income, right? So the slope of the Marshallian demand function with respect to I is constant, which is A times P1 to the power minus 1. And that is a linear function. So Engel's law does not hold when you have a Cobb-Douglas utility function.